Let's do another one of these examples. And for this problem, I will have to look back upon some earlier treatment of limits. Let's say that I want to add the fractions starting n equals 1, going to infinity, pretty typical stuff there. And my fractions will follow this formula. Numerator 2 to the power n squared, denominator n factorial. So just as a reminder, n factorial is the product of all the whole numbers starting at 1 and going up to n. Now, if I want to test this for convergence, do I want to integrate from 1 to infinity 2 to the power x squared all on, oh, I don't even know what x factorial would be. I mean, I do know, but it's not something we talk about in this class. So clearly not something I can expect of you. So let's see what happens when we try this using the root test. So the root test says we are going to calculate the limit of the ratio of successive terms. So as n goes to infinity, I'm going to look at the absolute value of the n plus first term in the list divided by the nth term in the list. And fortunately enough for me, all of these terms in the series are positive, so I don't need to worry about absolute values for this particular problem. Let me go ahead and write this as a product of two fractions. So I know that my n plus first term has the formula 2 to the power n plus 1 squared, all divided by n plus 1 factorial, right? Everywhere I saw an n before, that is now n plus 1 in parentheses. What am I going to do over here? Well, I'm supposed to be dividing. I'm dividing one fraction by another, so I'm going to multiply by the reciprocal of that fraction instead. Saves me a little bit of scratch work. The denominator now is going to be 2 to the power n squared, and the numerator is going to be n factorial. So let's see what happens. I want to cancel as much as possible, so let's see what I can do. For those 2's, there are more 2's in the numerator than there are in the denominator, right? N plus 1 squared is a larger number than n squared. How many 2's do I expect to see? Well, there will be n plus 1 of them, n plus 1 squared of them, and then I take away n squared of them. Simple enough. What do I do with these factorials? So this factorial up here in the numerator consists of all the whole numbers starting at 1, 2, 3, and so on, going all the way up to n, multiplied together. This factorial in the denominator is the very same thing, right? 1 times 2 times 3 times 4, all the way up to n plus 1. So when I divide one factorial by another in this way, what will I have left on my denominator? Just an n plus 1. Now, I'm almost ready to evaluate this limit. Let me clean up the formula for that exponent. Denominator is going to be n plus 1. Numerator, I'll have 2, and it'll be raised to the power 2n plus 1. So all I did was I FOILed out this exponent and I canceled my n squareds. It's also handy to remember that 2 square numbers differ by an odd number. So if this is n blocks over here on the side, this is n blocks down here on the bottom, then inside the square region here is n squared. And then here is my plus 1. Kind of a neat thing. Not exactly a calculus fact, but beautiful nonetheless. Now, I need to calculate what this limit is. And it looks like I've got a bunch of 2's on the numerator, and I've got just a single n plus 1 on the denominator. If you want to be super technical about this, we'll take a look at a continuous limit instead. As the variable x goes to infinity, I'll have 2 to the power 2x plus 1, all divided by x plus 1. Now, this is a limit we explicitly know how to deal with, but we should remember it from Calculus 1. Yes, that Calculus 1. Because the numerator is a continuous differentiable function, and the denominator is a continuous differentiable function. In the limit as x goes to infinity, my numerator goes to positive infinity. In the limit as x goes to infinity, my denominator also goes to positive infinity, so this is a case for L'Hopital's rule. So I'm going to replace the numerator by the derivative of the numerator. I'm going to replace the denominator by the derivative of the denominator. What is the derivative of x plus 1? Please remember that the derivative of x plus 1 is just 1. What is the derivative of 2 to the power 2x plus 1? A little bit trickier, but we can do it with the chain rule. The derivative of any exponential function is itself. I need to multiply by a constant depending on the base of the exponential function. So here, the natural logarithm of 2. I then need to multiply by the derivative of the function that is inside my chain of functions. The derivative of 2x plus 1 is 2. So what have I got? I am taking the limit as x goes to infinity of numerator 2 to the 2x plus 1 power times a constant. That's still going to infinity. Denominator is just 1. So this limit goes to infinity. So what do I do in the root and ratio tests when my limit that I'm checking goes to infinity? Well, I say that the series that I started out with diverges. The end.